Hello, welcome to our Unit 1, 1.2 lecture. This one should be pretty short and sweet. We're going to be jumping off of what we know about isotopes from last year and adding in a little bit of what's called mass spectroscopy. Basically, it has just to do with being able to read a graph. So I think we're going to be in the clear for today. All right, so again, we're in Unit 1. This is Learning Objective 1.2, Mass Spectroscopy of Elements. Now, the learning target itself only deals with the physical mass spec graphs, but I can't teach you that without reminding you about what isotopes are. Okay, so remember that, hang on. Isotopes are going to be atoms of an element that have, of course, the same number of protons and electrons because it is one element. So we could be talking about isotopes of sulfur. Okay, they're all going to have 16 protons, but they might have different number of neutrons. So that's the only way that isotopes are different. Okay, because of this, they're going to have the same chemical properties. Okay, they're going to react the same. They just have slightly different masses because of those neutrons in the nucleus. Right. So when you think mass spec, think isotopes. When you think isotopes, think one element, different masses. All right. How to identify isotopes? Here's a quick question for you to make sure that you are still able to see what would be an isotope pair and what would not. So really quick, answer the question on Edpuzzle. Which of these are examples of isotopes? All right. Hopefully you picked the second pair, are strontium, because those are the same element. They have different masses because of their different number of protons. Whereas our potassium and argon are not isotopes. They're two different elements with different number of protons. They happen to have the same masses because of their different number of neutrons. All right, we did this last year. There will be some practice problems on it if you need help with this, but I'm not going to spend a lot of time on it in this lecture. So finding our average atomic mass, remember this is a weighted average. So you're going to be multiplying the mass of an isotope by its percent abundance. And when we multiply using percents, we use the decimal form. So that's my first bullet point here. Remember, if it was 79%, make it 0.79. People do a pretty good job of that. It's the ones that are already decimals or are single-digit numbers that you tend to make a mistake. So like if it was a 2% abundance, make sure you put in 0.02. We're dividing by 100. Okay. And you may have more than two isotopes. The formula here only shows two isotopes, mass of isotope 1 and mass of isotope 2, but our ... means that there could be 3 or 4 or 5 isotopes depending on the element that you are dealing with. All right. All of that was just reviewed to get us to what is mass spectroscopy and how are we going to use it in AP chemistry. So this is the tool that we actually use to identify different isotopes. We don't just like wake up one morning and go, chlorine has 2 isotopes. I feel it in my heart, right? They do use some tests to figure that out. And the most important of those tests would be mass spectroscopy. So what they do is they make your atoms into ions. They throw them at a sensor, essentially. Okay. Our ions then can be sorted by mass because things of different mass are going to be moving at different angles when they're put through our beam of electrons, okay? So what that means is that you'll be able to see how many different masses there are. They actually use what's called a mass to charge ratio to determine that. But you're never going to have to figure out what that really means other than we sort based on that mass to charge ratio. And this is the data they use to then calculate that average atomic mass. So what does it look like? Here we have an element So let's say isotope 50 had a 4.3% abundance. You'll see at 50, halfway between our 48 and 52, we have a really short peak, okay? Our isotope 52 had an 84-ish% abundance, okay? That's our large peak. A short peak at isotope 53 and a short peak at isotope 54. So the first thing you can do when you look at a mass spec, you can say, you won't usually have this data table. This is just extrapolating. You would look at it and you would say there are 4 isotopes for this element. I know that because there are 4 different peaks. The left here is our relative abundance. So typically it's out of 100, so you can read it as percents. It doesn't need to be super exact. If they want you to do calculations, I imagine they would give you a table, or they would make it an easier graph to read, okay? On the x-axis, like I said, you can read it as your mass. It does technically measure your mass to charge ratio. So they call it the MZ ratio. So if a question asks about the MC ratio, they are just asking about the mass of those isotopes. Okay. Now, looking at this element, we would say that the mass, it has to be between 50 and 54. It's probably going to be closest to 52 because that's our most abundant and it's halfway in between our options. So if we look at our handy dandy periodic table, hopefully you guys still have one, we are looking between 50 and 54. Okay, it cannot be higher than 54 AMU. It cannot be less than 50. So our only options are vanadium, chromium, and not manganese, because manganese you see has a mass higher than 54. Okay, so we would look and we'd say, well, I guess, so 52 is my highest percentage anyways. This must be chromium. Done. You can identify your element based on the graph. Oh, it even says it there. Look at that. Chromium mass spectrum. I should have cut that out. And then your periodic table. Let's do one. So I want you guys in your ed puzzle to try and figure out what element this would be. All right. Hopefully you guys put that this was boron. As you can see, there's 2 isotopes for this element, one with a mass of 10, one with a mass of 11. The one with a mass of 11 is more abundant, and actually I would really like, I kind of want to edit it because it doesn't add up to 100% abundance, but that's fine. So closer to 11 than to 10. So that's how we got to boron. All right, my last, I think, close to last slide of the day. I just want to talk a little bit about chlorine. So I hope that you guys remember that chlorine is diatomic, which means it is found in its natural state as a pair, right? So here is a mass spectrum for chlorine. You can see that there are 2 peaks over here on the left at 35 and 37 AMU. And then over here we have a 70, a 72, and a 75. 1, 2, 3, 4, 74. Sorry. So why is that, right? Because chlorine is diatomic, it means there's a couple different ways that chlorine molecules can form and a difference what their mass will be. So if 2 chlorine 35s combine, then you would have a mass of 70. If a chlorine 35 and a chlorine 37 combine, you'll have this intermediate, and if it is 2 chlorine 37s, you'll have the higher. So it's just showing you how, because some elements are diatomic, your mass spectrum could be split into 2. My phone is ringing. Hang on.